Hi there, welcome along. Watching our pendulum swinging. So any mass on a spring moving from side to side is a pendulum. And this is performing your first example of oscillation. In the absence of friction, this just keeps going. When it's moved to the side, the combination of the tension in the string and the force of gravity moves it back to that central blue line. Talk more about the terminology in a moment, but that's the equilibrium position. But when it gets there, it's moving, there's nothing to stop it, so it moves out the other side, then the tension brings it back. So we get this pattern of oscillations. And there's really quite a lot of understanding and prediction, and we really do have a very good handle of this. It's actually one of the bits of physics quite good because although we do make some assumptions, we actually really can model the world quite nicely. So I've taken a screenshot of what we were just looking at. We can now start to develop some of the terminology. You can see this central blue dotted line. And that's where the pendulum would sit if it had no energy, if we just left it to hang. So we call that the equilibrium position. And if we think back about the work we did on structures last year, that makes total sense, because when it's in that position, the forces are all balanced and it's in equilibrium. That means that if it's got no energy, it will just sit there forever. But momentarily, as this thing moves sideways, it's moving sideways with constant velocity as it goes through the equilibrium, because the tension isn't pulling it one way or the other. If we look up here, we've got the protractor, and in the case of a pendulum, and we'll look at a mass on a spring in a moment, which is in some ways a little bit easier. The way that we measure how far the pendulum has moved to the side, we're going to talk about the angle it's moved to the side. I don't know why those menus are cropping up, sorry about that. There's our angle. That maximum angle there is called the amplitude. So the biggest displacement, or the biggest angle the oscillator gets to, is the amplitude. The thing that's changing all the time is the displacement. And the word displacement, just like last year, is a vector, meaning how far from its starting point has it travelled. Notice we're going to have we usually have a positive side and a negative side for displacement, and we would call our equilibrium line zero displacement. So now we'll have a look at the mass on a spring oscillator. So we're back in our little simulated environment, and what we've got here is a spring. You might want to remember from last year that we know about spring behaviour. The force in a spring is equal to the extension of the spring multiplied by the spring constant, or the stiffness of the spring. If you remember, and this is crucial, in a spring via Hooke's law, up to the elastic limit, the displacement is proportional to the amount of force in the spring. So we've got an unknown mass hanging on a spring, and that green line, thinking about the terminology we used before, represents the equilibrium position, doesn't it? So let's just displace it, and you can see, just like the pendulum, it's now performing a set of oscillations. So if it goes too high, the spring tension is a bit less than its weight, and the weight pulls it back down. When it goes low, the spring tension is greater than the weight, and it pulls it back up. It only balances it when it's going through the green line. So when it goes through the green line, momentarily it's in equilibrium and it's going at constant speed. We can make it perform larger oscillations, and we can make it perform smaller oscillations. So remember, the maximum distance of the top of that spring, which is where we're measuring the displacement to, is the amplitude, but the displacement itself is continually changing. Just going to pause it We'll return it to its equilibrium position. So we can ask ourselves a kind of practical question. If in ordinary years we might have got you actually physically to do this with a mass and a spring, but we can still tackle the question. What I'm going to do is set it oscillating, and then we're going to time the time for 10 oscillations so we can work out the time period. So the time period is the time taken for one complete oscillation. So I'm just going to grab hold of it. If this was at maximum positive displacement, if we take up displacements as positive, if the mass was to do this, then that's one complete oscillation. So it's going from its original position and back to it is one oscillation. For various reasons we'll probably speak more of in the future, we like to time an oscillation from the center, okay, from that position. So it takes a little bit of care. That's the start of the oscillation. That isn't the end of an oscillation, because although it's back in the same position, it's now going in the opposite direction. So one full oscillation is start, stop. Okay, so that's your complete oscillation. So I'll just put that into action. So I'm going to time 10. Top tip is to make sure that I say start or 0 when it first goes through the equilibrium position, and then I'll count away. So start, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's taken 15.33 seconds, meaning it's about 1.533 seconds for one oscillation. So a simple thing we can change, probably the simplest thing we can change, is what happens if we make the oscillations smaller. So we're actually going to do very small. We've done medium, then we'll do very big. Okay, so let's reset that. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 15.40. That's incredibly close to the previous time, isn't it? It's only different by 0.07 seconds, and that was for 10 oscillations. So I think we would say within experimental error, those are the same amounts of time. So I'm going to do it one more time with big oscillations. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I couldn't have done that if I'd ever do that again. So we've got 15.37. So the time now for one oscillation is 1.537. So our inescapable conclusion is, within experimental error, the length of time an oscillation takes for this oscillator does not depend on the size of the oscillations, and we call that isochronous behaviour. Iso meaning same, and chronous meaning same. And it turns out we're going to study a very important group of oscillators, and they're called the simple harmonic oscillators. And they all share a number of properties in common, one of them being that the size of the oscillation does not affect, or the amplitude of the oscillation does not affect the time period of the oscillation. And the thing they all have in common, which is why it's easiest to teach this from a spring, is the restoring force is proportional to the displacement. So if we pull it twice as far from equilibrium, then the restoring force towards equilibrium is twice as much. And I'll kind of do a quick slide on the maths of that. But that partly explains the phenomena, doesn't it? We would have thought these oscillations, being small, might take less time, but the oscillator gets to travel much more slowly because the spring has less tension, it gives it less acceleration, and it has less time to, and therefore it gains less speed because it's less tension, less acceleration. Put it all the way up here, and it now has a much bigger acceleration. So although it's got further to travel, it's travelling faster. So just a kind of quick little summary. We're studying a class of oscillators called simple harmonic oscillators. And the defining characteristic of a simple harmonic oscillator is the acceleration is proportional to the minus of the displacement. And sometimes you'll see it written or hear people say that the acceleration is proportional to the displacement, but they are in opposite directions, and that's a perfectly reasonable way of saying it, but that's what the role of the minus sign is for. The role of the minus sign is to change the direction or change the sense to make sure the acceleration and the displacement are in opposite directions. Let's just very briefly talk about a little bit more about that. So if this is our equilibrium position and we take above as positive and below as negative, there is no simple convention for that. If the oscillator is there, that's its displacement, and its displacement is clearly positive. It's on the positive side of the equilibrium. However, that object has a force back down in this direction, and that force will make it accelerate in this direction. So when it has a positive displacement, it has a negative acceleration. When it's down here, the displacement is negative, but the restoring force, the force pulling it back to equilibrium, and the acceleration are in the opposite direction. So here we have a positive displacement and a negative acceleration. Here we have a positive acceleration and a negative displacement. Let me just put the displacements in. So in other words, they're always in opposite directions.